Sup, everybody? Blah, blah, blah. I'm so cool. I'm like the coolest teacher I know. Sorry, guys. Anyway, so today we're going to go through our atomic structure homeworks. So I've set you guys 2 homeworks because I understand that ionization energies are really, really challenging. So I've set you guys a couple of homeworks. We've got a homework on successive ionization energy, and then we follow that up with ionization across a period and down a group. Okay, so I'm going to share my screen with you guys straight away. There we go. Go to that one. And then what I do is I then go to my notes. And now I disable my camera. And hopefully, oh, please don't crash. Please don't crash. Please don't crash. Yes! Come in. Getting good at this. Cool. Right. So, okay. So you guys can. Oh, I haven't actually got the YouTube video running, so that would be definitely something I ought to do. So let's see if I can get the YouTube video. Because I need the chat, don't I? Need to chat. YouTube, and it should come up with me being live, which would be there. We go. Boom. Yeah, chat. Whoa, stop. Go away. Cool. Right, there we go. Chat's up. Yeah, I'll pop it out. I'll pop out the chat window, and then I can close the video to save myself a little bit of CPU. There we go. Right, crack on. Let's get rid of that bad boy. Okay, so screen shared. Right, amazing. Okay. So you guys can mark this as you go along, and then as soon as we finish the first one, I'd like you guys to then pause the YouTube video. You can go away and complete the second one, and then come back and mark it and add to the score sheet. Amazing. Okay, so successive ionization energies first. So first one is completing the electronic configuration, and notice that they have given you an ion. Yeah, this is important. And they've given you a rather unusual ion as well, the 1+. So remember that whenever we're doing, I'm hoping that I'm sharing my screen. Am I not sharing my screen? I am sharing my screen. Okay. I think am I sharing my screen? Yes. Okay. Go to the periodic table. Remember, electronic configurations are about reading the table. Yeah, so we're going to go for magnesium, but we're going to make it a 1+ ion. So remember that hydrogen and helium are meant to be here. Yeah, so 1s2. Yeah, that brings us to the end. Back to the beginning. Going through this one, 2s2. Cross into the next bit. 2p6. And then back to the beginning. I really ought to use a different pen. It's just such garbage. And it's way too thick. Come on, Mr. Duncan. I'm gonna erase all that and make this a bit easier to see. Because I need you guys to be able to do this, and it's so important. Okay, let's try that again. We're looking for magnesium, but we're going to make it a 1+ ion. So 1s2, that covers these guys. Back to the beginning, 2s2, and then across into the next group, which is 2p6, hits neon, back to the beginning. So magnesium would be 3s2, but now we're going to make it magnesium 1+. We're going to remove 1 electron, and we're done. So there's my final answer. So we've got 1s2, 2s2, 2p6, 3s1, and we're done. 1 mark.Moving on. Next, state the meaning of the term first ionization energy. The minimum amount of energy, and yes, you need that minimum bit. Yeah, you have to say it because you can't just say the energy to remove, because that would mean anything from the minimum and up, and you must say the word minimum. The minimum amount of energy needed to remove 1 mole of electrons, 1 mole of electrons from 1 mole. Don't like that I've written a number, shouldn't do it. From 1 mole of gaseous magnesium atoms. Right, and then I'm gonna write an equation for that, magnesium atoms. I'm gonna write the equation for it because I think there's more value, magnesium atoms. So here's the equation, Mg gas going to Mg1+ gas and 1 electron. Oh yeah, from gaseous atoms to form Mg1+. Unipositive gaseous ions. Oh. I do want to add that, to be fair. By the way, just write the equation. It gets you 2 of the marks. I think that actually gives you all of them. No, it doesn't. It gets you 1 of them because you've got to say the minimum amount of energy needed to remove. Cool. So with that definition of the equation, I get both marks. It's definitely worthwhile learning how to do the equations because they're going to ask you to do that anyway. Write an equation including state symbol to show the reaction that occurs when the second ionization energy of magnesium is measured. Mg1 plus gas goes to Mg2 plus gas plus 1 electron. There's the second. Yeah, we've removed the first one already, and we're now removing the second. Oh, stop, Alexa. Alexa, stop. Alexa, stop. Sorry, folks, Alexa's being a tool. Next, explain why the second ionization energy of magnesium is greater than the first ionization of magnesium. Right. So we are removing magnesium, no charge, and we're going to form magnesium 1 plus, Mg1 plus gas. Yeah. Notice the size change. When you remove an electron, you always shrink. Then we're going to go from magnesium 1 plus gas down to, what was it? Magnesium 2 plus gas. Yeah. And that second one's going to be way harder. Yeah. So we're going to say the first reason is that you're in bullet points. Explain what, okay. When removing second electron, you are removing it from a +1 ion. Second bullet point. The 1 plus ion is smaller. The 1 plus ion is smaller. Electrons closer to the nucleus. Closer to nucleus, increased attraction. Attraction, more energy to remove. More energy to remove. I know that it appears like I'm running out of space. In reality, if I was writing this in an exam, I'd be shrinking my text so that it would fit on the lines. That is a very reasonable amount of space to write all that. But you definitely need all of that information. Yeah. So second ionization energy is a 1 plus ion, greater attraction. I should be moving from a 1 plus ion. So greater attraction. I'm going to put that as well. So greater attraction as well. Attraction, more energy. The 1 plus ion is smaller, electrons closer to the nucleus, increased attraction, more energy to remove. Yeah, I like it. I'm tempted to show you the mark scheme for that particular question. I can't be bothered. That's everything you need. You can decide, can I say more shielding? No, Anch, you can't. But they've done it deliberately, Anch. And I'll show you why. Because a magnesium atom, Mg atom. So we know that we've got 1s2, 2s2, 2p6, damn it, 2p6, 3s2. Oh, darn it, 3s2. Yeah. Okay, so if we remove the first one, Anch, here's what happens. Remove that electron there. What do we now have? That we now form, yeah. Oh, are we comparing? We're comparing greater than the first. Yeah, that's correct. So this one here is IE1, ionization energy 1 Anch. Would you agree? Yeah. But look what we're now removing it from. 2 electrons, 1s2, 2s2. Darn it, I've done it again. 2p6. Notice how I've shrunk it. 3s1. There you go. The shielding, Anch, is the same. Here's the shielding. Shield, 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 shield. The shielding is the same. If you go to the second ionization, if you go to the third ionization energy, yeah, if you go to, darn it. If we go to IE3, that's IE2. If we go to IE3, this is what it would now look like. Oh, that shell's gone. Right, now I'm removing it from 1s2, 2s2, 2p6. Now there's less shielding. 2p6. I'm now removing one of the electrons from an energy level closer to the nucleus. Now there's less shielding. Does that make sense, Anch? Yeah? So, no, you're not allowed to actually say that one. Something to bear in mind. Right, this question was really clever. So what they wanted you to do is they wanted you to be able to use your understanding to predict an ionization energy. Now, they give you a massive range for this, by the way, huge. But what they're trying to do is they're talking about magnesium. And what we realize is if we were to graph magnesium and to do its successive ionization energy, this is energy. Yeah, this is IEs 1 to 12. Yeah, IEs 1 to 12. What we're going to see is this. 1, 2, look at that. There's number 1. It's 736. It's now nearly doubled. So there's the step up to number 2. But now we realize that magnesium is in group 2. Number 3 is going to be absolutely massive. And we're then going to get a lovely successive 8. Yeah. And then the final 2. Jump again. Boom, boom. Yeah. And what we need to realize is that this 8 here, there's a nice consecutive rise. In the successives, we get this lovely steady increase. So if I was trying to predict this guy, if I'm trying to predict that one, what I can do is look at the difference in these guys. And this one here is approximately a 3,000 difference. So this one is going to be approximately 7,500. Whoop, whoop. There we go. By the way, the range is massive. It's like from 6,000 to 8,000, something like that. It's really big. But I hope that makes sense. Like, these questions are really tough. And this is why these homeworks are so important, because it allows me to put into context the understanding that goes with these graphs. And it's lovely to be able to see these rises and falls and understand the trends that we can use. Really clever. Next one, right, this one is, rather than predicting one, they're just using it to see a jump. So first, pretty tough. Second, yeah, tougher. Third, tougher. Fourth, tougher. Holy moly! Now, right, that there, guys, now that's a jump. What group am I in? I'm in group 4. Yeah, the graph would have looked like this. The graph's just gone boom, 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 boom. Yeah, that's what it's done. And remember, the number of electrons at the beginning are the outer shell electrons. Yeah, that was terrible. Yeah, these are the outer shell electrons, which means 4 in the outer shell, I'm in group 4. And it says period number 2. So I go to my beautiful periodic table. Oh, it's so beautiful. So gorgeous. Yeah, I'm going to go to my beautiful, gorgeous periodic table. Period number 2. Whoa, that was terrible, wasn't it? Period number 2. There we go. And group 4. Boom. I'm carbon, baby. There we go. Got carbon. Carbon. Hello, carbon. Next. Okay. Oh, bit of a mass spec question. It's always nice to have a bit of questions from previous topics. That's quite nice. Chlorine has 2 isotopes with a relative isotopic mass 35 and 37. 4 M over Z values are given below, which will occur in a mass spectrum of chlorine gas Cl2 from an ion with a single positive charge. Ooh, okay. So we definitely can't get Cl35.5 doesn't exist, but we could get that. We could get that if we had chlorine 35 bonded to chlorine 37, and it was a +2. If we did that, if I add that, I'm really curious to know what that adds up to. So if we did 35 plus 37 divided by M, remember, M over Z value, M over Z, mass, the total mass of this molecule here is 72, yeah, and the charge is plus 2. So if I go 72 divided by 2, I get 36. That's wrong. So that is not going to give me that. Lol. If I do 37 and 37, try that. So 37 plus 37, it gives me 74 divided by 2. 37. No, that doesn't work at all. That's just stupid. 35. Oh, that's weird, isn't it? So hang on a minute. Could I get it from a 1? Could I get it? I could get it from a +1, couldn't I? No, you can't get. Hang on a sec. Can I get 35.5 in chlorine gas if I had a +2? I thought 35 plus 37 divided by 2 gives me 36. Oh, you can't get it. Can you get 35.5? I thought you could. If I did... No, because they're just going to be bonded together. No, you cannot get 35.5. What a nightmare that is. Isn't that entertaining? Even with a +2 value, you can't get it. Because it's always going to come up as even numbers. You can get 36. You can't get 35.5. That's impossible. Never possible. 36. I can get 36. Because if I had 35 bonded to a 37, I've just been doing this. 35 plus 37. 35 plus 37 divided by 2. And I get 36. And that was a 2+ ion. Yeah, then I'm going to get 36. That is possible, but it says in the question, single positive charge. Can be B. No. Can I get 71? Could I? With a +1 charge. 35 plus 35. 35 is 70. Nope, can't get that. If I do 35 plus 30, that's 72. You can't get 71. Can't. Can he? 72, you definitely can get. Because 72, of course, is a chlorine 35 bonded to a chlorine 37 divided, with a 1+ charge. Yeah? So if I do 35 plus 37, that gives me 72. So that one can be done. Yeah, with a plus. Well, that makes sense. That's really hard. Holy moly, is that hard. Can I just point out, this one, impossible, but these ones are technically possible, but they're not 1+s. No, sorry, there's another impossible one. 71, impossible. Yeah, 36 is possible, but it would have to be a +2. That's really clever. Really lovely that. Love that question. God, that's hard. Right, next. The first 5 ionization energies of aluminium are shown below. The orbital from which the first 5 electrons are removed during ionization starts with... Right, hang on a minute. Aluminium. Aluminium is element number 13. 13 electrons. 1s2. I quite like these pictures. I've never done these before. 2s2. 2p6. How does that give me? Gives me 10. 3s2. And 3p1. I like it. Cool. So there's aluminium. We're going to remove aluminium's electrons one at a time. So the orbitals from which the first 5 electrons are removed during ionization, starting with the first electron, are, right. Going to remove him, number 1, from the 3p. Correct. So straight away, it ain't A and B. Yeah, it's either going to be C or D. Next electron comes from the 3s. That is correct. The next one then comes again from the D. Loving it. Loving it. That's genius. Genius. That's a, sorry. Hang on a sec. I just want to add, take that. I want to go, that one there would be IE1, ionization energy 1. Then there'll be a little bump. Yeah, as we get less shielding. That would be IE2. Yeah, and then this one doesn't actually matter, by the way. It would be either one of them in whichever order, but they're going to be from the same one. That's going to be IE3. Isn't that lovely? I love it. I love it. Genius. The answer is D. Moving on. It's really clever. Next, okay. Oh, it was so mean with this. So it's giving you an element X, and it says, what group am I in? Right. Hard, jump. And I know, by the way, I understand that people go, but hang on a minute, there's a jump here. And I'm like, it's a trap. The reason being is, if you're doing successive ionization energies, and you're removing the outer shell electrons. If you remove the first electron and you enter a new shell, well, you'd have you'd have 8 then to follow. Yeah, you'd never have 2 and a 2. That doesn't work. It would just go 2 and then into the next shell, which is going to have 8 in it. Unless you're in, by the way, unless you're in helium, and helium would just look like this. Yeah, but helium would also be like, it would be ridiculous, redonkulous jump. So that's him. So the first 3 electrons there, and then the next 8 are here. So it's a clever trap. So that tells us that it's in group number 3. It's in group 3B, because there are 3 electrons in outer shell. It's learning how to read consecutive graphs. That's what they're doing. The next, from the graph, it is possible to deduce the most stable ion of X. It will be, well, it's going to lose 3 electrons, so it's going to be X3+. That's really mean that. Can I just point out, Edexcel's choice on that question is evil, because if you lose 1, then you're going to lose 2. That's really mean that. Can't really get away from it, though. But Edexcel, thanks. Thanks, Edexcel. FedExcel. When aluminium 4+ ion is formed, the forced electron is lost from where? Okay, let's run it again. Aluminium, 1s2, 2s2. I quite like these diagrams. They're quite nice. 2p6. I'm going to go aluminium as entirety, by the way. 3s2, 3p1. I like it. Right, we're going to remove the first. Remove the second. Remove the third. Remove the fourth. Okay. So the 4th electron is lost from 4th IE. There it is. There's IE4. It's coming out of the 2p. I'm done. It's clever that. By the way, I've never used those diagrams before. It's kind of new for me, this. And it works quite nicely just to see how they come out. I quite like them. Some value in it. Right, I love this. Isoelectronic. The word iso in chemistry means same. So isotopes, same identity. Topes is identity. Isomers, same part. Iso is same. Mer means part. Merman, part man. Mermaid, part woman. You get the point. But this is iso, so same electrons. That's what that translates to. So let's write out the EC for each of these. So we've got lithium. So we've got lithium 1+. So 1s2, 2s1. There's lithium. Let's now turn it into its ion. Turn it into its ion. Lose it. So final answer, 1s2. O2-. So that's going to be 8 electrons for oxygen originally. 1s2, 2s2. 2p4 is the original oxygen, but it gains 2 electrons. Okay, so they are definitely not the same. Next, sodium 1+. Sodium is number 11. So Na+ is going to be 1s2, 2s2, 2p6, 3s1 for sodium, but it's a positive ion, so we lose this one. Next one, chloride ion. So a chloride, for chlorine, which is element number 17, 1s2, 2s2, 2p6, back to the beginning, 3s2, skip over, 3p, I need to get to 17, 3p5, but it's now an ion, gain an electron. They are definitely not the same. Next, magnesium 2+. These get quicker, by the way, the more you do them. So Mg2+. What's magnesium is element number 12. 1s2, 2s2, 2p6, 3s2 original, but it's an ion. Remove its electrons. Sulfide ion, element number 16. 1s2, this is s2 minus, 1s2, 2s2, 2p6, 3s2, 3p6, 4, no, hang on a sec. Oh, sulfide. Hang on a minute. Sulfide. Oh, element number 16. It's just before chlorine. So 3p4. I like it. Okay? Tables ways. I love that table. So there you go. 3p4. That's sulfur. But remember, it's an ion. It gains 2 electrons. Definitely not the same. Aluminium 3+, fluoride. I'm running out of space. I'll lay it underneath it. Aluminium, element number 13. Yeah, 1s2, 2s2, 2p6, 3s2, 3p1. There's aluminium. But it's an ion. Lose it, lose it. Final answer. Fluoride. Fluoride is element number 9, I believe. 1s2, 2s2, 2p5. But it's an ion. Add an electron, and their configurations are isoelectronic. And I'm done. The answer was D. Man, that took a lot of work. Anyway, next. This is by far the hardest question on the homework. This is tough, man. I went through this with Anch on a Google Hangout chat because he sent me a message and asked me for some support. So I went through it with him on a Google Hangout. Only took me like 5 minutes, but it was really hard. And I understood why he was wanting a bit of one-to-one feedback. So that was cool. Well done, Anch, for communicating with me, asking me for some help. So, okay, first thing is element X and Y are in the same group. Just going to get rid of that, by the way. Are in the same group. What group are they in? Please, chemistry teacher. That was weird. Sorry. Okay, so number 1, X. Whoa! Jump. Next one. Harder, hard. Sorry. Easy, bit tougher, bit tougher, bit tougher, bit tougher. Whoa! Jump. They're both in group 5. Both in group 5. Okay. Where is group 5? I love my table. Love my table. They're both in group 5. Okay. So let's highlight group 5. Okay. Next. So we know they're in there somewhere. Next. Who are my choices? Right. I've got antimony, arsenic, selenium, and tellurium. Okay. They could absolutely be any one of those. Yeah. So let's just quickly have a look. So the first 6 ionization energies. Fine. Where are we? Table. Right. So number 1. Oh, okay. That's funny. Because tellurium and selenium are in the wrong group. So let's eliminate those bad boys. Don't need you and you. Yeah, that's garbage. So the only ones in group 5 are antimony and arsenic. Right. The next thing to realize is they've given us them either way round. So what does this now look like? We both know that they're in group 5, but if you notice, if I was to graph these two, X, the graph of X, graph of X would look like this. This is graph X. There we go. And so let's draw a little line of best fit. There we go. C group 5. And this is X. Let's now graph Y. Y is harder. 1,000. 1,800. 27. 43. Hang on. 27. 4,800. 6,000. And then 12. Right. So what that tells us is that it is harder to remove Y's and harder and easier to remove X. Well, hang on a minute. That's really clever. Because if they're in the same group, the easier electrons means further out. It means further out. So it's antimony and arsenic we're focusing now on because they're the ones that are in the question. And what we realize is that antimony, shell, antinomy's electrons are further out from the nucleus. That there is the 3, that's the 1, 2, 3, 4, 5. This is the 5p. Yeah, this is the 5p subshell. Yeah, and whereas arsenic's outermost electrons are in the 4p. It will be harder to remove the 4p. They're closer to the nucleus, less shielding. Right. So antinomy is easier to remove. Antinomy is easier to remove. There's antimony. Antimony. And this one must therefore be arsenic. Arsenic. So arsenic is harder because it's closer. Let's just check that. Arsenic close to the nucleus, harder to remove. That makes total sense. So X is antimony and Y is arsenic. The answer is A. Now that is a grade A star question. Holy guacamole. What they have done in that, holy guacamoles, holy moles. What they've done is they've combined consecutive ionization energies with ionization energy down a group. That is hard. Holy mackerel. Right. Holy moles. Let's keep going. The electronic configuration of 5 atoms A to E. Arrange these atoms in order of increasing molar first ionization energy. Right, increasing. So we want the easiest and then the easier further out. Further out. Yeah, so that one's going to be the easiest. E is going to be the easiest. E. Next one. The next one's going to be D. Let's graph it. That's interesting, isn't it? Oh, okay. Hang on a sec. They're in the same period, aren't they? Yeah, except for A. A is it because look, this is really clever. It's really hard. It's linking in my other bit. So shell 2, shell 2, shell 2, shell 2. B, C, D, and E are all in the same period. They're in period number 2. So if I plot the ionization energies across a period, I just always know that graph. Got my lovely little bumps and dips and bumps. Yep. There we go. So we can clearly see that E is this guy. We can then see that D is this guy. We can then see that C is this guy. And then B is this guy. It's a trap. Oh, it's such a trap. Holy moly. So it goes from easiest to highest. So it goes E, and then D, and then B, and then C. That's such a trap. Oh, I'm so sorry, folks. You wouldn't have been able to do that question without having done the next lesson on YouTube. That's hard, that, man. It's really tough. And the last one, of course, is A, because A is helium. Helium's up here. Yeah, so A is the last one. Very hard. We're moving from the first shell. It's right next to the nucleus. That's well hard. That's really tough, that, guys. Really, really tough. Sorry about that. Shouldn't have been there. I've added the wrong question. Next, state giving a reason for your choice with one of the following gives the first 4 ionization energies of silicon. Okay. So W. Easy. Whoa, jump. Holy guac. Guys, look at that. What? It's massive. It's gone up by 4,000 and the next one's only gone up by 3. That's an enormous jump. So that's in group number 1. Yeah, group 1. Next one. Easy, harder. Whoa! Massive. That's group 3. Next. Easy, harder. Whoa! That's huge. It's group 2. Yeah, next one. No real jump. It's group 4. It's group 4. There's no massive jump here, guys. Look at that. For Z, they've got to 4,000, and they've done that with W in the second one. You know, that's ridiculous. That's group 4. It's Z is silicon. Yeah, letter Z. Reasoning. Steady increase in ionization energy. Steady. I'll say silicon has 4 electrons in its outer shell. Silicon has 4 electrons in its outer shell. Sorry, that was terrible. 4. No, don't try that again. Silicon has 4 electrons in its outer energy level. Outer energy level. Energy level. And therefore, there's no increase. There's no sudden increase. Z shows no sudden increase. Sudden increase. So electrons have all been removed from same shell. I'll do. Hard that. Clever. Clever, 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 clever. Next, what time does this lesson finish, by the way? I am very aware that this is taking a lot longer than I was expecting it to. Let's have a look. You've got 11:15, this finishes. Okay. And we're at the end. Blimey, that last question, by the way, guys, is going to be only 2 marks, I believe. 1 mark for Z, and then 1 mark for simply saying Z shows no sudden increase in electrons, all have been removed from the same shell. That's actually the marks. That's going to be the marks there. It's only 1 mark. There you go. Right, guys, this has taken me longer than I thought it was. And so what I'm actually going to do is at this point is it's been a really, really interesting homework. These are all exam questions from Edexcel, and it's just showing you just what level they're expecting you to be working at. Can I now ask everyone on the classroom? Oh, hang on a minute. Take that question out of the total marks. CBD, isn't C the lowest on the graph and thus the easiest? Oh no! If I made a mistake. Oh no, what have I done? Hi, oh no! Damn it! A should go there. Thank you, Louis. Thank you, he's the hardest. No, hang on a sec. No. Arrange these atoms in order of increase. No, A is going to be the hardest. A. No, that's correct. C. No, the easiest is no. Louis, he's gonna. Oh, hang on a sec. Oh, I've completely messed that question up. I've completely stuffed that question up, folks. It's such a horrible question because it says going from okay, number 1, who's going to be the easiest to remove? C. Oh, I can't believe Louis just beat me. Who's going to be the next hardest? B. Who's going to be the next hardest? D. Who's going to be the next hardest? E. And who's going to be the hardest is A. I'm so sorry. Louis just beat me. Ugh! I was too busy trying to explain it. I'm sorry. You know what? There's no excuse. I did a mess of that. It's totally my fault. I even did it backwards and everything. It's a nightmare. I'm sorry, guys. Yeah, so that's the final answer. I'm sorry. It was really hard. Yeah, apologies. Right. I'm going to end the lesson there, folks. So I'm going to end the YouTube video here. Next lesson, I'll go through the other homework. And then, guys, I'm afraid you have your test. Right. So the first thing I need to do is go back to my sheet, re-enable my camera, enable device. Don't crash. Done. Then I can go back to StreamYard, and I can bring you guys back, and then go start camera. Go for the front one. Yes! Getting good at this. Right, guys, I'm back. I hope you found that useful, folks. I made a mess of that question. I do apologize. It was tough. It was the fact that you were having to think through the process, and I should really take that out of the marks, but I'm not going to, Ange. Louis got it. Louis beat me. So, yeah, thank you, Louis, for being on the ball there, because that would have been an absolute disaster if I'd made that mistake without correcting it. Thank you, Louis. Really appreciate it. Guys, I'm going to see you all next lesson. I hope you have a lovely weekend. And can you have a go at doing the homework, please, for ionization energy across the group and drop it. Bad day. Across a period and down the group. I'll see you guys soon.